Hello everyone, I'm Lijie from Tsinghua University. Today I am very happy to present my joint work, Almost Everywhere Circuit Lower Bounds from Non-Trivial Derandomization with Lijie, Chen, and Ryan Williams from MIT. First, I will give some motivation of our work. For a given function f, let f sub n denote the restriction of f to n-bit inputs. Let C denote a typical collection of functions, where each C sub n contains functions from n-bit inputs to 1-bit outputs. For example, C could be a circuit class such as ACC0 or the set of low-degree F2 polynomials. We will define ACC0 later. We consider two different lower bounds notions. The first one is the infinitely open separation. This is the notion that is widely studied. We say that f is not in C if there are infinitely many n such that f sub n is not in C sub n. The second one is the almost everywhere separation. Say that f is not in infinitely open C if for every sufficiently large n, f sub n is not in C sub n. Compared with the infinitely open separations, almost everywhere separations are stronger and more satisfying. For example, Williams proved in 2011 that there is a language L in nexp non-deterministic exponential time, such that L does not have polynomial-sized ACC0 circuits, and hence nexp is not in ACC0. However, despite the huge impact of this result, it only provides an infinitely open separation. So it could be the case that the language L is only hard on extremely rare input length. Practically, such a situation is not very different from that nexp is in ACC0. Since 1980s, there were a series of circuit lower bounds established by combinatorial or algebraic methods. Typical examples include superpolynomial lower bounds for AC0, established in a line of beautiful works, and superpolynomial lower bounds for AC0 parity, proved by Rasborov and Smolensky. Here, AC0 is a class of constant depth circuits with AND or gates of unbounded fan-in and NOT gates. AC0 parity is AC0 circuits extended with mod 2 gates. These lower bounds mainly depend on combinatorial and algebraic ideas. They argue for each input length individually, and they usually extend to the almost everywhere separations naturally. Unfortunately, using combinatorial and algebraic methods alone only yields relatively weak lower bounds. They are often subject to the natural proof barrier. So, for example, it had been open for more than 20 years whether ACC0 can compute nexp before the question was finally resolved by Williams' algorithmic method in 2011. In structural complexity theory, people are able to prove some lower bounds against stronger circuit classes, but for complexity classes much larger than P. For example, the fixed polynomial size lower bounds of the class MP to the MP proved by Cannon, and the class MA with 1 bit of the Wise proved by Sentinel. The third example is a superpolynomial lower bounds for ACC0 circuits, proved by Williams' algorithmic method. We will discuss the algorithmic method in detail later. All of three examples argue for different input lengths simultaneously. Such argument usually involves proof by contradiction and case-by-case analysis. It is widely open whether these lower bounds can be extended to corresponding almost everywhere separations. Now let's turn to the algorithmic method. In 2010, Williams initiated a new program in circuit lower bounds study, which aims at proving lower bounds by designing non-trivial circuit analysis algorithms. Perhaps the most well-known result derived from this framework is the breakthrough that nexp, non-deterministic exponential time, is not computable by ACC0 circuits. This result was later improved to the much smaller class NQP and extended to the average case. We will discuss it in the next slides. Roughly speaking, the main spirit of the algorithmic method is that one can prove circuit lower bounds by designing non-trivial circuit analysis algorithms. Typical examples of circuit analysis tasks include SAT, sharp SAT, and CAP. Let me introduce these problems. For each of these problems, we are given a circuit capital C on n-bit input. In the SAT problem, we want to decide if there is some satisfying input to capital C. That is an input x such that C of x equals 1. In the sharp SAT problem, we want to count the number of satisfying inputs to C. In the CAP problem, we want to estimate the number of satisfying inputs within an additive error of epsilon times 2 to the n. Here CAP stands for Circuit Acceptance Probability Problem. It is a canonical derandomization problem. By non-trivial, we mean that the algorithm only needs to run a little bit faster than the 2 to the n time brute force algorithm. In the following, we give 3 more examples on the applications of the algorithmic method. The first example. First, some definitions. Let NQP stand for the class non-deterministic quasi-polynomial time. That is, languages that can be decided by non-deterministic machines in 2 to the polylog n time. Let ACC denote constant depth circuits with n or mod m gets of unbounded fan-in and NOT gates, where m is a fixed constant. There was a line of work towards proving average case lower bounds of NQP against ACC zero circuits, culminating in the result that NQP cannot be half plus 1 over poly n approximated by polynomial signed ACC circuits. That is to say, one can find a function f in NQP such that, for infinitely many n, every small ACC zero circuit cannot compute f sub n correctly on more than half plus 1 over poly n times 2 to the n inputs. What's the algorithm? The algorithm behind this lower bound is a slightly faster sharp-set algorithm for sub-exponential size ACC zero circuit. Compared to the 2 to the n time brute force, this algorithm has a 2 to the n to the epsilon saving in running time. The second example. Consider the finite field F2 for an n by n matrix M over F2 and a rank parameter R. The R rigidity of M is the minimum number of entries one needs to change in M to make its rank to become at most R. So, having a large R rigidity means being far away from low-rank matrices. The construction of rigid matrices has close connections to communication complexity and arithmetic circuit lower bounds, as observed by Rasborov and Valiant. In 2019, Ellman and Chen proved a remarkable result, a P to the NP construction of rigid matrices by using algorithmic method, which has parameters incomparable to all previous results based on combinatorial and algebraic methods. They showed that, for infinitely many n, their algorithm can construct an n by n matrix that is far away from any matrix of low rank. The rank parameter was later improved to 2 to the log n to the 1 minus epsilon by Bangel et al. If we think of low-rank matrices as a special circuit class, their result can be viewed as an average case lower bounds for this class. The algorithm behind this lower bounds is a fast sharp-set algorithm for low-rank matrices, which takes as input the low-rank decomposition of a matrix and counts the number of ones in the matrix in time slightly less than n squared. The last example. A probabilistic F2 polynomial is just a distribution over F2 polynomials. Say such a distribution computes a function f if for every input x, a random polynomial drawn from the distribution computes f of x correctly with probability over 2/3. The degree of a probabilistic polynomial is just the maximum degree in its part. In 1980s, Rasborov proved omega of square root n degree lower bounds for probabilistic F2 polynomials. Since then, it had been open for decades whether these lower bounds can be improved. In 2020, Viola proved via the algorithmic method nearly linear probabilistic degree lower bounds. Just like the 2 previous examples, case lower bounds only hold infinitely often. The algorithm behind this lower bound is a non-trivial sharp-set algorithm for low-degree F2 polynomials, which again runs slightly faster than the brute force algorithm. Now we discuss our new results. We show that all of the previous e to the np lower bounds proved by the algorithmic method can in fact be extended to hold almost everywhere. First, we extend the general connection. That is, we show that non-trivial circuit analysis algorithms can in fact imply almost everywhere e to the np lower bounds. As applications, we extend 3 results discussed before, including the strong average case ACC0 lower bounds, the probabilistic degree lower bound, and the EP to the NP construction of rigid matrices. We discuss 3 new results in order. The first one, strong average case lower ACC0 lower bounds. In recent work, Chen and Ren showed that NQP cannot be half plus 1 over poly n approximated by polynomial size ACC circuits. Their work focuses on the class NQP, but for the much larger class e to the np, Their results only works infinitely often, and their method cannot achieve sub-exponential parameters. So for the larger class e to the np, we improve their work from both sides. That is, we show that e to the np cannot be half plus inverse sub-exponential approximated by sub-exponential size ACC circuits, even infinitely often. The better inapproximability parameter is obtained by using a new hardness amplification theorem, improving a technique of Chen and Ren. Unfortunately, I don't have enough time to cover the new hardness amplification. Please check our paper for the details. As a corollary, we give an almost everywhere e to the np pseudorandom generator construction for ACC0 with only a polylog seed length. This is achieved by combining our average case lower bounds with Nissan-Wiggson's standard PRG construction. To compare, the deterministic PRG construction for AC0 with polylog seed length is known before. However, the deterministic construction for AC0 parity is a hard open question. Currently, no sublinear seed length PRG for AC0 parity is known. Given access to an NP oracle, our construction only has a polylog seed length and works for the stronger circuit class ACC0. The second one, e to the np probabilistic degree lower bounds. Recall the e to the np nearly linear probabilistic degree lower bounds proved by Viola. This result only works infinitely often. We extend it to the almost everywhere setting with the same lower bounds parameter. That is, we give an e to the np language capital L such that for all sufficiently large n, L sub n requires probabilistic F2 polynomials of nearly linear degree. The last one, P to the np construction of rigid matrices. Recall we have discussed the rigid matrix construction by Elman and Chen, and later improved by Bangel et al. We extend it to the almost everywhere setting without compromise on parameters. For all sufficiently large n, our algorithm outputs an n by n matrix that is far away from matrices of rank at most 2 to the log n to the 1 minus epsilon. Next, we briefly review the infinitely often lower bounds proof and explain how we extend it to the almost everywhere setting. We will use the worst case e to the np lower bounds for ACC0 as an example. First, we review the original proof from a slightly different view. This slightly different view will be very useful in the extension to proving almost everywhere lower bounds. So first, by the n-time hierarchy, we have a language L hard in n time 2 to the n that cannot be computed in n time 2 to the n over n. We consider computing this language L hard. So first, we can compute the language by its definition. We guess a witness of length 2 to the n and verify its correctness. This can be done in time roughly 2 to the n, matching the n-time hierarchy statement. A crucial observation is that if the witness is given as the truth table of some small ACC circuit, capital C, then the verification can be accelerated to time 2 to the n over super poly n. This is achieved by using a short, efficient PCP so that we can reduce the verification task to solving set for ACC0. Then we can use the presumed non-trivial set algorithm for ACC0 to speed up the verification. The proof of this part is quite involved. Fortunately, in discussing our new result, we can use this part as a black box. So given this claim, we consider the possibility of cheating in the computation of L-hard by only verifying witnesses that are truth tables of small ACC circuits. Of course, we know that we cannot really compute L-hard by doing so, or we will contradict to the n-time hierarchy theorem. We will show later that the failure of the cheating algorithm indicates that a correct witness is corresponding to a hard function against small ACC0 circuits. Now, formally, we design an algorithm A-cheat which wants to cheat in the computation of L-hard by only verifying witnesses of small ACC circuits. That is, A-cheat guesses a sub-exponential size ACC circuit capital C and verifies if the truth table of capital C is the correct witness for A-hard of X. This algorithm runs in time 2 to the n over super poly n. By the n-time hierarchy theorem, A-cheat cannot decide L-hard. Also, since A-cheat is trying to compute L-hard by considering a subset of all valid proofs, we know that it can only make one-sided error. Namely, if A-hard of X equals 0, then A-cheat of X equals 0 also. So there are infinitely many X such that A-cheat of X equals 0, but A-hard of X equals 1. For every such x, we know that there exists a correct witness for a hard of x. However, it cannot be computed by small ACC circuits. The reason is simple. If the witness could be computed by a small circuit, then H8 could guess that circuit and pass the verification, which contradicts to that H8 of x equals 0. So in other words, a hard of x can separate its correct witness from all small ACC circuits. Note that in e to the np, we can compute the witness for a hard of x easily. So this is how we could separate e to the np from ACC 0. Now let's try to construct the hard e to the np language. First, we give an e to the np algorithm that takes a short advice. The algorithm takes as input an n-bit index I. The advice to the algorithm is an n-bit string x sub n. Here x sub n is supposed to be a string such that H8 of x sub n equals 0 and a hard of x sub n equals 1. By the n-time hierarchy theorem, for infinitely many n, we can find at least one such x sub n. Also, there might be some input length n such that there is no valid x sub n. Since we are proving an infinitely open separation now, for such n, we just set x sub n to an arbitrary but fixed string. Next, the algorithm uses an NP oracle to find the lexicographically first witness y for x sub n in L hard and outputs the ith bit of y. We have argued that if H8 of x equals 0, then the string y cannot be computed by any sub-exponential size ACC circuit. So therefore, for infinitely many n, given the correct advice, the algorithm computes a hard function that does not have a sub-exponential size ACC circuit. We also observe that the advice is not necessary. Since x is relatively short, we can put x in a part of the input. This expands the input length from n to 2 times n. The sub-exponential hardness is preserved in this process. Looking at the proof, it depends crucially on the n-time hierarchy theorem. In the proof, we design and compare two algorithms, H8 and A hard. Only by the n-time hierarchy, we can show that there are infinitely many strings x such that H8 of x and A hard of x do not agree. The separation is achieved by computing correct witness for A hard of x, which cannot be computed by any small ACC circuit. If we have an almost everywhere version of the n-time hierarchy with the same parameters, then the same argument immediately yields the almost everywhere separation of e to the np from ACC. Unfortunately, proving an almost everywhere n-time hierarchy is also a notoriously hard open question. It is even open whether nx is in infinitely open np. Luckily, looking at the literature, we find that there is an almost everywhere n-time hierarchy theorem against bounded witness computation. Formally, let n-time guess T of n, G of n denote the class of languages that can be decided by non-deterministic algorithms in order of T time, which guess no more than G of n bits of witness. In 2016, Fortnall and Sathnam showed that there is a hard language in n-time guess T of n that is not in infinitely often n-time guess little o of T of n, little o of n. That is, if we only want hardness against faster algorithms which guess sublinear length witness, then there is an almost everywhere n-time hierarchy. Next, we try to use this theorem to prove the almost everywhere separation. A similar argument applies. Here we choose the time bound T of n to be n to the k. Recall in the infinitely often separation, the time bound is chosen to be 2 to the n. It will be clear later why we choose T of n as a polynomial this time. We choose Fortnall and Sathnam's hard language in n time T of n, denoted by L hard. Let's compute L hard. First, we can compute L hard by guessing a T of n bits witness and verify it. This runs in time roughly T of n. Again, if the proof is given as a truth table of a small ACC circuit, we can speed up the verification. For brevity, we set a parameter L as log T of n, which is roughly k log n. We consider the cheating algorithm H8. H8 guesses an ACC circuit capital C of a size sub-exponential in L and verifies if the truth table of capital C is the correct witness for A hard of x, using the non-trivial set algorithm for ACC. This can be done in time 2 to the L over super poly L. Now we explain why we choose T of n to be a polynomial. Note that for our choice of T, sub-exponential in L implies sublinear in n. So we only need a sublinear number of bits to describe the circuit capital C. So it follows that H8 computes a language in n time guess little o of T of n, little o of n. By Fortnite and Tsinhua's theorem, a cheat cannot really compute L hard. Moreover, for every sufficiently large n, there is an n-bit string x such that a cheat of x equals 0 and a hard of x equals 1. Similarly, we know that the correct witness to a hard of x cannot be computed by small ACC circuits. Now let's try to construct the hard e to the MP language. We put two algorithms here for reference. A hard compute L hard faithfully by guessing a witness of left T(n) and verify it. And a cheat is trying to cheat by only considering witnesses that are truth tables of small ACC circuits. Again, we give an e to the MP algorithm with advice. The input to the algorithm is an L-bit string I. The advice to the algorithm is an n-bit string x sub n, such that a cheat of x sub n equals 0 and a hard of x sub n equals 1. Here n is roughly 2 to the L over k, so that log t of n equals k log n, which in turn equals L. Unlike the infinitely open separation, for every sufficiently large L, a valid advice x sub n always exists. This is guaranteed by Fortnite and Tsinhua's theorem. The algorithm uses an NP oracle to find the lexicographically first witness y for x sub n and outputs the ith bit of y. We have argued that if a cheat of x equals 0, then the string y cannot be computed by any sub-exponential size ACC circuit. Therefore, for all sufficiently large L, given an n-bit advice, this algorithm computes a hard function that does not have a sub-exponential size ACC circuit. Unfortunately, it is not easy to eliminate the advice. In particular, the previous trick does not apply. We cannot take x sub n as a part of the input, since it is too long. The hardness from y is sub-exponential in L. Note that n is already exponential in L. So we can only get a trivial sublinear lower bound if we take x sub n as a part of the input. Here comes our key observation. With access to an NP oracle, we can find a useful advice by ourselves. More precisely, for Fortnite and Tsinhua's hard language, we construct a refuter that can explicitly refute any weak algorithm that claims to decide L hard on every sufficiently large input length n. Formally, the refuter takes as input an integer n and the description of some weak algorithm A. By weak, we mean that the algorithm runs in n-time guess little of t of n, little of n. In order of n times t of n time with access to an NP oracle, the refuter finds an n-bit string x such that a of x does not compute L hard correctly. We are ready to construct the final e to the NP language. We also put two algorithms here for reference. The correct algorithm, a hard, and the cheating one, a cheat. This time, we construct an e to the NP algorithm without advice. The algorithm takes an L-bit string I as input. It sets n as roughly 2 to the L over k, so that L equals log n to the k, which in turn equals to log n t of n. The algorithm uses our new refuter to find an n-bit string x sub n such that a cheat of x sub n and a hard of x sub n do not agree. We have argued that it must be the case that a cheat of x sub n equals 0 and a hard of x sub n equals 1. Then it finds the lexicographically first witness for x sub n and outputs the ith bit of the witness. The algorithm runs in time polynomial in n, which is bounded by 2 to the order of L. To show the hardness, we can use similar argument. That is, since a hard of x sub n equals 1 and a cheat of x sub n equals 0, we know that the correct witness for a hard of x sub n cannot be computed by any small ACC circuit. In summary, we showed that there is a language in e to the NP that cannot be computed by sub-exponential size ACC circuits, even infinitely often. We propose an open question and conclude our talk. We have shown almost everywhere lower bounds of e to the NP against ACC 0. The natural next step would be to show that an expert is not computable by ACC 0, even infinitely often. We believe our work will be useful in proving this. However, it seems that substantially new ideas are required to achieve this. Thank you for listening.